This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Topic 09. The Brayton cycle. Gas turbines. Very high yield. Expect 2 or 3 questions. Brayton is Rankine's gas phase cousin. Same 4-device closure, but air instead of water. Pressure ratio instead of saturation tables. Ideal gas relations instead of steam table interpolation. If you mastered Rankine, this comes fast. Here's the problem. An ideal cold air standard Brayton cycle. Air enters the compressor at 100 kilopascals and 300 Kelvin. Pressure ratio 8. Max cycle temperature at the turbine inlet 1200 Kelvin. Cold air standard means constant CP and gamma. Both compressor and turbine are isentropic. Find the thermal efficiency, back work ratio, and net specific work. Classic PE exam setup. Pressure ratio and max temperature set every answer. Concept. A Brayton cycle is 4 devices in closure, like Rankine, but gas instead of water. The compressor compresses ambient air isentropically to high pressure. The combustor adds heat at constant pressure, burning fuel with the air. The turbine expands the hot gas back to low pressure for shaft work. Some runs the compressor, the rest is net output. Heat rejection goes to the atmosphere in an open cycle, or a heat exchanger in a closed one. Same analysis either way. Brayton on the TS diagram has 4 states. 1. Compressor inlet, atmospheric air. 2. Compressor exit, same entropy, higher temperature and pressure. 3. Turbine inlet, peak temperature after combustion, still high pressure. 4. Turbine exit, same entropy as 3, back at low pressure. 2 isobars bracket 2 isentropic legs. The enclosed area is net work per unit mass. The key relation, for an isentropic ideal gas process, the temperature ratio is the pressure ratio to the power gamma minus 1 over gamma, the formula that ties Brayton together. Setup. Each device is a steady flow energy balance, kinetic and potential energy dropped. For an ideal gas, every enthalpy change is Cp times temperature change. So compressor work, combustor heat, turbine work, and heat rejection are each Cp times the relevant temperature difference. Net work is turbine minus compressor work. Efficiency is net work over heat in. Back work ratio is compressor over turbine work. The compressor eats 40 to 60% of the turbine's output. First law closure gives net work as heat in minus heat out. The isentropic temperature ratio shortcut. For an ideal gas isentropic process, the temperature ratio equals the pressure ratio to the power gamma minus 1 over gamma. For air, 0.286. So T2 over T1 is that. The turbine leg is 1 over it. The closed form efficiency drops out, 1 minus 1 over the pressure ratio to the gamma exponent. It depends only on pressure ratio and gamma, not on inlet or max temperature. The headline Brayton result. Variable table. 4 state columns, 1 per device junction. Given, pressures at 1 and 3, temperatures at 1 and 3. Compute T2 from the isentropic compression, T4 from the expansion. Then 4 process quantities: compressor work, heat in, turbine work, heat out, and net work, efficiency, back work ratio last. Under cold air standard, 4 temperatures solve the whole cycle, no enthalpy lookups, much faster than Rankine. Pattern recognition. Gas turbine, Brayton cycle, or air standard analysis puts you in topic 09. Pressure ratio is the primary parameter. Max cycle temperature, pin state 3. Regeneration, or exhaust heat recovery, preheats the compressor discharge with turbine exhaust, lowering combustion heat and boosting efficiency by up to 10 points at moderate pressure ratios. Intercooled and reheat split the compressor and turbine into stages. Isentropic efficiencies below 1 mean topic 06 corrections. Jet engines are open cycle Brayton with thrust as the output. Handbook quick reference covers the isentropic ideal gas relation, the Brayton section, and the compressor and turbine balances. Memorized air values under cold air standard. Cp around 1.00, Cv around 0.72, gamma 1.4, exponent 0.286. Gas tables with variable Cp are more accurate above 1500 Kelvin, but need 4 more lookups. For PE Brayton problems, cold air standard is almost always good enough. Solve. State 1 is given. Compressor exit. T2 is T1 times the pressure ratio to the gamma exponent, about 543 Kelvin. Compressor work is Cp times delta T, about 245 kilojoules per kilogram. Pro tip: compute that gamma exponent factor once and reuse it for states 2 and 4. State 3 is given. Combustor heat is Cp times T3 minus T2, about 660 kilojoules per kilogram. State 4. The turbine drops T3 by the same factor, about 663 Kelvin, typical exhaust. Turbine work is Cp times the temperature drop, about 540. Sanity check: T4 should always exceed T1. If not, you slipped arithmetically. Step 3. The three metrics. Net work is about 296 kilojoules per kilogram. Efficiency 44.8%. Back work ratio 45%. The compressor consumes almost half the turbine's output. Why gas turbines need very high max temperatures. 2 free cross-checks. The closed form efficiency matches, and first law closure matches net work to heat in minus heat out. Final answers. Efficiency 44.8%, back work ratio 0.45. Net specific work about 296 kilojoules per kilogram. The Carnot ceiling here is 75%, so Brayton captures about 60% of it, typical. A telling comparison: a Rankine plant at a much lower 500 Celsius max gets about 38%. This Brayton at 1200 Kelvin gets 45. Gas turbines scale better with max temperature, while combined cycle plants stack both. Side note on regeneration: an ideal regenerator uses turbine exhaust heat to preheat the compressor discharge, boosting efficiency. The closed form becomes 1 minus T1 over T3 times the pressure ratio to the gamma exponent. For our numbers, lifting efficiency from 45 to 55%. But there's a gotcha. At high pressure ratios, T4 drops below T2, so the regenerator would cool the combustor feed. The crossover is where T4 equals T2. Recognize it so you don't apply regeneration blindly. Traps. 5 ways Brayton problems lose points. 1. The isentropic exponent is gamma minus 1 over gamma, not gamma. For air, 0.286. 2. Absolute temperature is always Kelvin in the T over P relation. 3. Don't forget back work. Net work subtracts compressor work, nearly half the turbines. 4. Regeneration only helps below the crossover. Check T4 above T2 first. 5. Cold air standard drifts above 1500 Kelvin. If the problem says gas tables, don't shortcut. Quick recall: 4 states, 2 isobars, 2 isentropic legs. Temperature ratio equals pressure ratio to the gamma exponent, 0.286 for air. Closed form efficiency is 1 minus 1 over that. Device works are Cp times temperature change under cold air standard. Cycle metrics come from the 4 temperatures, and regeneration boosts efficiency, but only below the crossover pressure ratio. Master these, and you master Brayton. Next up, Topic 10. Vapor compression refrigeration. Reverse a Rankine cycle and swap water for a refrigerant. Evaporator, compressor, condenser, expansion valve. We'll walk the full pH diagram with R134A and compute COP. Before then, a question. With T1 and T3 fixed, what pressure ratio maximizes net work, not efficiency? Set the derivative of net work over pressure ratio to 0. The optimum is the temperature ratio to the power gamma over 2 times gamma minus 1. PEPrepengine.com/beta. The Brayton cheat sheet, the worked problem PDF, and a 5-question quiz are attached to this video. If the course helps you, subscribe.
The full study guide, with every equation and common exam trap, is free at PEPrepengine.com. Link in the description. Machine design, HVAC, structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.